Okay, so today we are talking about the difference quotient. So I think it's important that you understand like the motivation behind like what we're doing, so it doesn't seem like we're just doing some random expression for no good reason whatsoever. So I'm going to talk a little bit about the theory and like what the point of this whole thing is, but then we're going to mostly focus just on simplifying these guys. So the difference quotient is basically the basis for calculus. It's where the definition of the derivative comes from. And so when you get to calculus, you'll be doing tons of these. And I think it's important that you work on the algebra of it so that by the time you get to calculus, you're not getting hung up on distributing negatives and things like that. And you can focus on like what it actually means and where it leads you. So we're going to focus a lot on just simplifying these in this class, just so you get really good at that part of it, and then can extend that to the concepts that it actually applies to in calculus. But we are going to look at where it comes from and what it actually is, so that we understand why the heck we care. So I'm going to start with the graph of y equals f of x. And all that statement means is that if you're given some function named f, in practice we would be given like an equation like f of x equals 3x plus 5. So if you're given some function named f, that on the graph of that function you get the y coordinate of any point just by evaluating the function for whatever the x coordinate is, right? So this is just how we relate a graph to function notation. So we're just going to do some random graph, like doesn't really matter what it looks like at this point. And I'm going to put 2 points on that graph. And I'm going to call the x value of the first point just x. So how do we represent the y value of that? Yeah, it's just f of x, right? It's the function evaluated for the x value, which in this case is just x. So we'll call our y coordinate f of x. And then I'm going to pick another point over here, and like I'm just going to say it's some other point that's like bigger by h units. So h is just the distance between the two x values. So if my first x value is x and my second one is h units bigger, how could I write my second x value? Yep, it's just x plus h, right? It's h more than x. So then what would that y value look like? Absolutely, very good. So f of x plus h. And make sure that your parentheses are in the same place mine are. So we haven't talked about this for a while, but remember way back when how we talked about how there's a difference between like adding h to the input and then evaluating the function, and evaluating the function and then adding h to the output. Right, we like did a few of those where we had like f of a plus h and then f of a plus h. So make sure, like this all kind of falls apart if we don't write what we mean, because then we'll start doing the wrong thing. So it's f evaluated for an input of x plus h. So just make sure your parentheses are around that x plus h. And so the idea behind the difference quotient is that it's an average rate of change. So we've done this before. We have found the average rate of change in f from the point with an x value of x to the point with an x value of x plus h. And remember, when we found average rate of change, that was just, we basically just used the slope formula, right? The average rate of change is the change in the y values divided by the change in the x values. So we have 2 points here. The leftmost point has an x value of x and a y value of f of x. And the rightmost point has an x value of x plus h and a y value of f of x plus h. So we're finding the difference in the y values divided by the difference in the x values, which we've called average rate of change. We also have noticed that that's just the slope. Whoa. Whoa, there it goes. Of the line that passes through those 2 points, right? So we talked about how the average rate of change formula and the slope formula are essentially the same thing. They both have the change in our output divided by the change in our input. So for the change in our output, we're just going to subtract our 2 y values. So we have f of x plus h is our rightmost y value minus f of x is our leftmost y value. And then to find the change in our inputs, we're going to subtract our x values. So our rightmost x value minus our leftmost x value. And that's going to give us, well, I can't simplify the numerator because remember that f of x plus h and f of x are like individual values, and I can't do anything with them unless I actually know what those values are, right? That symbol isn't multiplication or anything like that, so you can't do calculations with it unless you actually have a value that it's equal to. So just like when we did like net change and average rate of change, we had to figure out what each of those was before we could subtract. So same thing here. There's nothing you can do to simplify this at this point, so we're just going to rewrite it. F of x plus h minus f of x. But then in my denominator, well, x plus h minus x is just h, yeah? Because x minus x is 0. And that makes sense because we set it up so that the difference in our x values was h, right? That's kind of how we started, was we were like, okay, let's have them differ by this, whatever we call h. And this expression, this f of x plus h minus f of x over h, is what we call the difference quotient. And the idea, just like real quick, without getting too deep into it, the idea behind the derivative is that you can't find the slope of a line without 2 points, right? Like you can't find, using a single point, you can't find the slope of a line. But it's often like it would be really handy if we could talk about like how steep a function is at one specific point, right? Because remember when we did average rate of change, we were like, it matters like which 2 points you're in between, and all we could do was average between those 2 points. And it would be really cool if we could be like, oh, this right here, this graph is this steep. That's what the derivative does for us. It sort of tells us what we call an instantaneous rate of change, which is like the slope at a single point, which we know we can't calculate, right? Because you'd be dividing by 0. Your change in x would be 0. So when we find the derivative, we take that second point and we move it infinitely close to the first point and do what's called a limit, which gets us as close as possible to being a single point. So eventually that h is going to be 0. But we won't do that yet. We will just simplify these. So that's sort of like, that's just the motivation behind all of this. And like I said, we're going to focus mostly just on simplifying these guys so you can get really good at that. And then you'll get to get deeper into the theory when you get to calculus. This formula is, so when we actually are given a function, we can evaluate what f of x plus h and f of x are to simplify more, but that formula is the same basic formula every time. And we just change it based on what f and f of x are. So we don't have to like develop this over and over again. And we'll always give it to you on a test. You don't have to like memorize what the difference quotient is. Any questions just like on how we got there or what this is? Yes?
So you don't have to make like denominators in order to subtract there because it's just x?
Right. So those are actually your x values. Whereas in the numerator, we don't actually know what our y values are. Like we don't have an expression for them, which we're about to. Once we're given an equation for f of x, then we'll be able to actually evaluate those and subtract them, which is what we'll do to simplify. But in the denominator, we actually have x values. They're not just part of a bigger symbol. Okay, let's simplify some of these guys. It's so fun. Difference quotients are just super satisfying because they get really, really messy, but then they get really, really nice and neat at the end. They all turn out pretty, which is, it's just satisfying. You get to like cross stuff off and have it work out nicely. So let's find the difference. I'm going to just write the instructions for all of these, so I don't have to write it every single time. But this is what the instructions will look like on a test. I don't know if I don't think I say find. I did say find. Okay. Let's find. I feel like sometimes we say evaluate. F of x plus h minus f of x over h for each of the following. Okay. Let's do f of x equals 5x plus 4. So I'm going to claim that we already know the answer to this is 5, and that you can know that even without doing any calculus. How do I know it's 5? Without doing any calculus. I know, but you have to learn calculus to do. Like, you have to take calculus class in order to know that. Knowing just what we've learned in this class, how do I know the answer is 5? There is no magic in math. Well, what did we say it was? We said it was an average rate of change, right? Is what the difference quotient was, which is the same as the slope. So if my graph was a line, wouldn't the average rate of change be the same no matter what? Mm-hmm. No matter which points I use? And the slope of this line is 5, right? And so the average rate of change is going to be 5 no matter what. So no matter what x values I choose to put in, I'm always going to get 5, which means the difference quotient has to be equal to 5 because it is the average rate of change in the function between 2 points. It's just kind of nice to know what the answer is going to be before you get started. It's only true of linear functions, though, because linear functions are the only functions with a constant average rate of change. And so they're the only functions where the quotient rule is always going to give you the same answer, regardless of your x values. So let's do it, though. And then we'll do ones that are nonlinear, so we don't know the answer ahead of time. So when you guys set these up, you're always going to write the formula on the left. And you don't have to write it every single time, but you do need to write it on the first line because we have lots of stuff going on. Here, I'm going to color code it this first time. And we don't want to get mixed up about what it is we're finding, especially when you get to calculus and you're doing this as part of a bigger problem, right? And there'll be lots of things going on and more to do afterwards. So you want to know what you found when you find it. So remember I've been kind of harping on you guys about using function notation when you do average rate of change? This is kind of what we've been building up to, is if you've been using function notation this whole time with your two sets of brackets, this is exactly the same process. We're going to do one big set of brackets here. And my function says do 5 times your input plus 4. When you look at this expression right here, what is the input? Just the input of that function. Yeah, it's just x plus h, right? Remember, the input is just whatever is in the parentheses. And so I want to do 5 times my input plus 4. And then in that second piece of it, well, my input's always just going to be x, which is what I'm given in the function itself, right, is f evaluated for an input of x. So that one you can really just copy. Okay, now time to simplify. The trickiest part of all this is just the distributing, like when to drop brackets and when to drop parentheses and stuff like that can get a little bit confusing. So I always look to the left of the left symbol to decide if I can drop them or not. So if I look right here, is there anything to distribute? No, so that means I can drop that set of brackets without doing anything, like it can just disappear. What about to the left of those parentheses? Is there anything to distribute? I have to distribute that 5 in order to get rid of those parentheses, right? So this is going to be 5x plus 5h plus 4. And I just dropped the square brackets because there was nothing to distribute. And then what about here? I have to distribute that negative to get rid of those brackets. So minus 5x minus 4. And then, like I said, these things always end up working out really nicely. And because of that, you can kind of check along the way to make sure you didn't make any mistakes. If you distributed everything correctly, when you get to this point, everything that doesn't contain an h should add to 0. So we have 5x minus 5x is 0, and 4 minus 4 is 0. And the only thing is left, or the only thing that's left, is terms that contain an h. I'm not saying that everything that contains an x will go away, although that happened here. I'm just saying things that don't contain an h will go away. So it's possible to have both an x and an h in a term. And so that turns out really nice and gives us 5h over h. And this is the second place where you can kind of check to make sure you didn't make any mistakes. H's will always cancel. If those two things don't happen, you probably made a sign error or some other distributing error. And we got 5 just like we said. Come on, it's a little satisfying, right? It simplifies all the way down to just little 5. Okay, should we do one that's not linear? Okay, so this one, like, I know it's not linear because it's got an x squared in it, right? So I can't just look at it and figure out what the answer is going to be. But now that we have some practice simplifying it, we can go in with confidence, right? So we have f of x plus h minus f of x over h. So my function says 3 times the input minus the input squared. So this first one, my first term has an input of x plus h. So we're going to do 3 times x plus h minus x plus h squared. And then my second term has an input of x. So we have 3 times x minus x squared. And everybody's over h. So now, same thing with the distributing. We want to look to the left of each symbol before we decide to drop it. So there's nothing to distribute here, which means I can drop those brackets without doing anything. I have to distribute the 3 in order to get rid of those parentheses. And then this next one's a little tricky because I have x plus h squared, which I have to do first, right? But notice that I can't get rid of the parentheses because I still have to distribute that negative, right? So I can't get rid of the parentheses until that negative gets distributed. So I'm going to come down here and do x plus h squared. This is one of the things you'll do over and over and you'll just memorize it. But remember from our first example today when we did that true-false, I can't just square the x and square the h. I have to actually multiply x plus h by x plus h. So we get x squared plus xh plus xh plus h squared. So x squared plus 2xh plus h squared. So we have minus, and again, I can't drop those parentheses yet because I didn't do everything to the left. So we have x squared plus 2xh plus h squared minus, sorry, that 2 got a little away from me. And then I look to the left of these parentheses. I have a negative, so if I distribute the negative, I can get rid of the parentheses. So we have 3x plus x squared, then all over h. And now I'll distribute that negative to get rid of the parentheses. So 3x plus 3h minus x squared minus 2xh minus h squared minus 3x plus x squared. And just when it seems like it's getting out of control, things are going to get nice and neat. So I have 3x minus 3x is 0. Negative x squared plus x squared is 0. And that's it. So 3h minus 2xh minus h squared. So notice everything that's left contains a factor of h. Right? Everything else added to 0. Can I cancel this h? Is it a factor of the top?
You can take an h out of the top.
Right, very good. So I can't just cancel it because it's part of a term, right? Not a factor. Like the entire, remember last week, we said if you have addition, subtraction, that whole thing is grouped. And if you can factor something out of the whole thing, then you can cancel it. So in this case, every term has an h. So that's our GCF. And now we can cancel it because we're able to factor the entire numerator as h times something. And we get 3 minus 2x plus h.
Isn't it still minus 8?
Oh, it is. Oh, thank you. that on purpose to keep you on your toes. Testing you. Just scoop up. What questions do you have?
That's it.
That's it. You guys want to try one? Sure you do. Minus f of x all over h. Whoa. So remember, when we have function notation, whatever is in the parentheses is your input. So our function says 2 times your input squared minus your input plus 3. So in this first term, what's in the parentheses is x plus h. So that's my input. So we're going to do 2 times our input squared minus our input plus 3. And then for f of x, we have x in the parentheses, so that says your input is x. So again, 2 times the input minus the input plus 3. And this whole thing over h. So now we get to start simplifying. There is nothing to the left of that left-hand bracket, so I can just drop those square brackets in that first set of square brackets. But then I see that there's a 2 here, which means I can't drop the parentheses until I distribute the 2. So I have to do x plus h times x plus h first. We did that in the last problem. So we know it's x squared plus 2xh plus h squared. And then I can't drop that second set of parentheses until I distribute the negative, right? And there's nothing I have to do before distributing the negative, so I'll just do that right away. And then I can drop the second set of square brackets if I distribute that negative. Whoa. All over h. So now I'll distribute my 2. And then just copy everything else. Oh, that was not a straight line. There we go. Over h. And so now we can combine like terms. So we have 2x squared minus 2x squared is 0. Negative x plus x is 0. 3 minus 3 is 0. And that's all we've got as far as like terms. So we get 4xh plus 2h squared minus h all over h. And again, we can't cancel anything yet because remember this whole thing is grouped, but we do see a GCF of h. So we have h times 4x plus 2h minus 1 all over h, and now we get to cancel that h. to get 4x plus 2h minus 1. If you find, oh, go ahead.
Does it matter if it's in descending order? Like,
No, because, so like with 4x and 2h, there isn't really a descending order because they don't have the same variable.
okay.
Like those are both degree 1. So if you were to switch them, it wouldn't really
It wouldn't do
change the,
anything, yeah.
like, the order as far as the degree goes. In general, when we talk about descending order in terms of like multivariable polynomials, we usually go in descending order of one of the variables. So like if you have like an x squared and an xh, the x squared will come before the xh because there's two x's and then one x. But for the most part, descending order only really matters when we're factoring. And here, the only thing you'll ever actually factor is to factor out that h. Because kind of our goal is to get to cancel that h off. So anything else that's going on as far as whether we can or can't factor doesn't really matter to us because there's nothing at the bottom that would cancel anyway. And the purpose for us factoring here is to simplify the fraction. So you don't really have to worry about it with these. Other questions? So one hint on these is if you keep getting 1 every single time, then you're adding the h, like you're doing f of x and then adding the h to the end instead of actually inputting x plus h in as your input. So if you get 1 every time, there's a very specific error that causes that, which is somewhat common. I promise you the answer is not always 1. I wouldn't do that to you. Otherwise, we'd just write 1 every time, right? Like, why bother with all this? So if you keep getting 1 over and over, just come see me so we can go over that specific mistake so that we can just correct it. It's a quick fix, but it's just a common one that comes up fairly often. I have a couple more papers to get back to you.